Hey everyone, so let's solve this Leetcode hard problem, earliest possible day of full bloom. So like the problem is pretty much on the medium side only. So let's see the problem statement. So we are given n flower seeds, and now for each seed we are given two integers, that is plant time as well as grow time. Now plant time denotes the means this ith seed, how much time it is taking to get planted successfully, and then it will be like the grow time of I will be denoting the number of full days it takes for the ith seed to grow after being completely planted. Okay, and once it has been planted as well as grown, the next day it will be blooming. Okay, so now we are given these two plant times as well as grow times array, and we are starting at day 0, and we can plant the seeds in any order. Okay, and we can plant it like suppose its plant time is 4, so we can plant it in 2 days here and then 2 days later as well. Okay, so this like we do not need to plant it in a continuous fashion. Okay, now we need to return the earliest possible day where all seeds are blooming. Okay, so for example, if we have this as the given input, that the plant times are 1, 4 and 3, and grow times are 2, 3 and 1. So we'll start from day 0. We can plant this day, means this seed, 0th seed, at day 0. So it will be taking 1 day for the planting, then it will be taking 2 days for the growing. So it will be taking 2 days for growing, and on the third day it will bloom. Okay, similarly for the second, means for this first seed, what will see, we will be taking 4 days for the planting phase, then it will be taking 3 days for the growing phase, and on the next day it will be blooming. And similarly for this seed, it will be taking 3 days for the planting phase, and then 1 day for growing, and then on the next day it will bloom. So in this case, like if we plant these seeds in this particular fashion, then 9 will be the minimum day at which all the flowers have already bloomed. Okay, so hence the output in this case is simply 9. So one thing that we need to make an observations first is, let's try to see. So we are given plant time and we are given grow time. Okay, so obviously we need to plant all seeds. Okay, we need to plant all seeds, and in one day I can only work on a single seed. I can only work on a single seed. Okay, this is sure, because we are given that in a single day we can only plant a single seed, and means we need to plant all the seeds. So the total number of time, means minimum time that we'll need for planting, it will be what? It will be simply summation of plant time of I, right? Because planting each seed, we need to plant each seeds in different days, and obviously if we want to plant it in the optimal fashion, so we'll be planting it in such a manner that 0th day we plant this, then for 3 days 4 days we plant this tree, and then for 3 days we plant this seed. Okay, so obviously it will be simply the minimum planting time overall, it will be simply 1 plus 4 plus 3. Okay, so which is means 8 here, so total 8 days. Okay, so I hope like this thing is clear. Now once we have already planted these seeds, what will happen is the seeds that we have planted earlier would have begun to grow, right? Would have begun to grow, and they will be growing phase. Okay, so when we planted, means suppose at this period of time the planting of a particular seed was completed, so they will start growing now. Okay, again means a new seed, suppose it was plantation was completed here, so again it will continue growing. So one thing we observed, like this plant time will be the fixed, means this overall time will be fixed. Okay, now based on the last plant that we have planted, because we can plant these seeds that we are given in any order, suppose it was 1, 4, 3, so either we can means do first 3 then 1 plus 4. Okay, so we can do that, means we can do it in any fashion, and the grow time was 2, 3, 1, 2, 3 and 1. So we can do that in any fashion, because obviously we know like the total planting time will still remain the same, means it doesn't matter in what manner, means in what order we are planting the seeds. Okay, so this time is fixed. Now what extra time will be requiring, we need to identify that, means is there some time which will be requiring for the growing phase, which for the trees, for the seeds which have all means not already completed their growing phase. Okay, so we need to find this time. So what will be like the most, like which seed will be affecting this grow time by the most factor? So obviously the seed which was planted at the latest time, it will be means it is it can be seen that its growing time will be means remaining. Okay, so this will be having a major effect on the remaining growing time. Okay, now suppose this was a seed which was planted earlier. So this seed would have been planting phase has been completed here, so it would have suppose a less effect on the growing phase, right? Obviously, because it has been planted earlier, means if we see like if its growing time is less than the, if it is growing time is greater than the last growing time. So obviously we see that the last seed that we planted, it will be like have more effect on extra time that we need for blooming, that we need, because obviously the summation of plant time of 5 will require definitely, but once we have planted this last seed, the time amount of time it will take to grow this last seed will need to add that to our result as well, right? Because this will be like the overall time will be this plant time plus this result. Okay, so now which means how planting means the last seed, we can plant any seed at this last value, right? We can plant any seeds at this last value because its end is fixed, its end is fixed, so we can plant any seed at here. So what will be like the most optimal seed to plant, most optimal seed to plant at end? So obviously, since what do we want? We want to means reduce the extra growing time that will be means that is here. We'll want to reduce it as minimum as possible. So obviously, the last plant that we'll be planting is should have a grow time as small as possible. Okay. So obviously means to minimize the overall time required for all the flowers to bloom, we should means plant the last seed which has the smallest grow time. Okay, so that as soon as its completion is means planting is completed, it is not requiring a lot of time to get its means growing completed. Okay, so we want to minimize it as small as possible. So one thing is clear, that planting seeds on the basis of decreasing order of grow time is feasible. Why? Because the last seed that we plant, it should require very small time so that the extra time is left. And the first seed that we planted, it can have a very large growing time because it has this liberty of utilizing this time, right? So it can have a very large growing period as well. So the first seed that we should plant optimally should be the seed which has the largest growing time. Okay, and the last seed that we should plant should be the one which has the smallest growing time. Okay, now you might think like suppose if we have this seed which completed here, whose completed planting was completed here, and it has a, since it has a growing time greater, so what if this growing time greater was means if this seed was ending at its growing time was ending here, so what if its growing time is greater? So means if it is greater, then we'll account that here. But we have placed the seeds in the most optimal manner, because obviously if we plant the seed further ahead, then obviously this right bound is going to increase only. Okay, so we have already placed this in the most optimal fashion because we have already sorted it on the basis of decreasing order of grow times. Okay, so obviously means the seed which has the largest growing time would already have been completed growing. Okay, because we have planted it in the leftmost side only, and a seed which has the smallest growing time would be left, and it will have means causing a very small effect on the extra time that we need. Okay, so what we can do here is it is clear that we need to sort grow times on the basis of decreasing order. Okay, now once we have sorted grow times on the basis of decreasing order, we want to find the maximum right bound. Okay, we want to find this maximum right bound that we can have. Okay, so what will be this maximum right bound? It will be simply what? It will be simply the means the time at which any plant is getting completed, the plant time at which any seed is getting planted completed, plus the grow time required for it. Now even if this grow period is very large, it will have a new level, new right bound. Okay, so right bound will be simply what? It will be simply the planting completion time of seed, planting completion of time of seed plus the grow time of seed, grow time of I. And this grow time we have already sorted it on the basis of decreasing order, so that means this planting completion time is as small as possible, so that we means the overall right bound is like smaller. Okay, so this is what we'll do. We simply sort the basis on the basis of grow times in the basis of decreasing order, and then for um, each seed we'll find this value. That is the means we'll maintain the current time and the prefix match that we have. Suppose the output input here was 1, 4 and 3, and the growing time was 2, 3, 1. So once we sort it, it will become on the basis of decreasing order, so it will become 3, 2 and 1. And for 3 we have 4, for 2 we have 1, and for 1 we have 3. So these are the planting times that we have. Okay, so for this, what will be the required means? So it will be the right bound will be simply at 4 time it will be getting planted, and plus 3 will be the total time here. So it will be 7 in this case. Now this will be getting means completed at what time? 4 plus 1, because it will be started at 4. So it will be getting planted completed at time 5, and 5 plus 2 again it will be 7. Okay, and now at what time this planting will be getting completed? It will be 5 plus 3 8, and 8 plus 1 9. So hence we'll find out the right bounds of each seed and then take the maximum right bound that we get, and hence in this case the right bound is 9, and that is like the optimal output here that we need to return. Okay, so I hope the algorithm is clear. We simply need to sort it on the basis of decreasing order of grow times, and for each seed we'll find out the current completion time of this seed based on like we have already planted all the seeds from 0 to I minus 1. Then what will be the planting completion time of this particular seed, and we'll add the grow time of this particular seed, and that will be like the right bound for this current seed. Okay, so I hope like the algorithm is clear, as well as like how we greedily tried to approach it. We saw like placing a seed on with the smallest growing time on the right was the most feasible thing to do, because it will have the smallest effect on the right one. Okay, so let's see the implementation. Like the approach is pretty simple. What do you do? We need to sort it on the basis of grow time, so we also need the excess of plant time as well. So you simply create this vector of pairs and push the grow time in the first and then plant time. Now we sort it on the basis of decreasing order, so that this grow time with the largest grow time comes first. Now the prefix time is simply like the completion time that we have for the ith seed. Okay, so it will be getting added at each step, means that we will be adding the plant time. Now this prefix time stores the completion plant completion time for this ith seed. Okay, and at each step what we want to find the rightmost bound. So rightmost bound will be simply the planting completion time plus error of I dot first, and which is storing the grow time of I. So it will be finding the maximum right bound and will simply return this maximum bound. And that's why I said like it is like not much on the harder side. It is like a medium only. Once we like saw this observation that we need to plant it on the basis of decreasing order of grow times, then like the implementation as well as the means the problem of the solution of the problem is pretty simple. Okay, so let's try to submit this code here and see how much time it takes to run. Like since we know like the n can go up to 1e5 here, so obviously the overall complexity is n log n, and it runs in 96 ms and beats 19% of the solution only. Let's see the most optimal one. So here it has also like created a map to store it on the basis of like sorted order, and then it is increasing. So it has like a greater complexity, but still it runs faster. So means our solution is optimal, so we know that. Okay, so I hope you were able to like grasp the logic behind the problem, and if you did, make sure to like as well as subscribe. And if you yet have any doubts remaining in any of like the parts discussed, then make sure to comment down. I will be happy to respond. Thank you so much for watching.